My name is Zach Shwirat-Conti, and I'm a Turing Research Fellow at the Alan Turing Institute in London. I would also like to introduce my colleague and co-organizer of the seminar series, Andrea Pizzaferrato, who is a visiting academic here at the Turing. And for those of you who are not familiar with the Turing, this is UK's National Institute for Data Science and AI. Additionally, if you are interested in sharing your work in any of our upcoming seminars, please feel free to reach out to Andrea or myself. Finally, some housekeeping. Questions may be asked towards the end of the seminar through the chat function or by raising your hand, unless, of course, our speaker for today does not mind questions as we go along. Right, so I'll hand over to Andrea, and I thank you all.
Thank you, Zach. Our speaker today is Paris Perdikaris. Paris holds a master's degree in applied mathematics from Brown University and another in naval architecture and marine engineering from the National Technical University of Athens. He completed his PhD in applied mathematics at Brown University in 2015. Following this, he worked as a postdoctoral research associate at MIT until 2017. Paris is serving as an associate professor at the University of Pennsylvania before his current position as a principal research manager at Microsoft Research AI for Science Initiative, where he focuses on foundations models for weather and climate modeling. His research interests span computational science and engineering. More specifically, his current projects include physics-informed machine learning, uncertainty quantification in deep learning, engineering and design optimization, and non-invasive medical diagnostics. Thank you again, Paris, for joining us. Today, he's going to talk about PirateNets, physics-informed deep learning with residual adaptive networks. And without further ado, the floor is yours.
Great. Thank you very much, Zach and Andrea, for having me here today, and thanks everyone for joining. So today I'll actually be presenting some work that was recently completed by my group at the University of Pennsylvania, and I'd like to highlight Sifan Wang, who has really led this effort. So this is work on physics-informed neural networks and basically introducing a new building block, a new architecture, along with an initialization scheme for improving the robustness and accuracy of physics-informed neural networks. So let me just jump right into it and maybe start from some high-level motivation. What I basically describe here as physics-informed machine learning is the use and the application of machine learning tools in applications where we have a lot of prior knowledge in place. And potentially we want to leverage this prior knowledge to compensate potentially for the lack of data. So we all know that currently, big deep learning models shine in domains where you have access to tons of data. However, there's many target applications in the physical sciences and in engineering sciences where you may not have a lot of data in place, primarily because the cost of data acquisition is very high. You may need to conduct very expensive experiments or simulations. But at the same time, you may want to try building machine learning methods that leverage some form of inductive bias to compensate for that lack of data and try to encode physical laws in them. So when it comes to inductive bias in machine learning, there's different sources that one could bring in such constraints. One, of course, would be to start and use large data sets if you have access to them. For instance, in domains like weather forecasting and climate modeling, there is actually a wealth of observations, and arguably physics is encoded in those observations. Many of those observations are outputs of numerical weather prediction models that are physics-based. So in those large volumes of data, there is culprits and fingerprints of the underlying physics. Similarly, in domains where you have maybe less data, you could think of using techniques like data augmentation to sort of leverage certain properties of the problem and maybe certain symmetries and sort of virtually increase the size of your data set and enable the training of large models. And alternative ways is to actually carefully revisit the model architecture and try to bake in inductive biases by designing appropriate modules and layers, for instance, equivariant layers that ensure that your model will respect certain symmetries of the problem and so forth. And then finally, what I would call the easy way out, another way of biasing a machine learning model towards some given constraint is by formulating training objectives and then penalizing basically the predictions of the model during training. In this way, you can encourage a model to satisfy some constraints in a soft manner, approximately. And this last bullet is the focus of this talk, because this idea of physics-informed neural networks primarily relies on training neural networks with training objectives that ensure that the predictions of a neural network will satisfy approximately a set of given constraints that come into the form of differential equations describing the evolution of some dynamical system. So let me give you a little bit of a historical perspective of physics-informed neural networks, because it's not a new idea at all, and it actually dates back all the way to the early 90s. Not surprising, a lot of the great work in neural nets was done back then. So at least as far as I know, the earliest work that I'm aware of is the work of Psychodios and Unger. They were chemical engineers at the time, and they were trying to build a neural network that leveraged first principles to model chemical processes. And then a couple of years later, I think the idea of using neural nets for solving ordinary and partial differential equations was formalized by this paper by Lagaris, Likas, and Fotiadis. But then sort of like the neural network winter came and nothing happened over the next 1 or 2 decades. And then there was a paper in 2017 that appeared with my co-authors, Mazia Raisi and George Kaniadakis, that kind of basically revisited those ideas from the 90s. So intellectually, there's nothing new here. It's the same old idea of basically using a neural network to represent the solution of an ODE or a PDE. So you have some differential equation that is given. So here n denotes some general, let's say, nonlinear differential operator. U is the latent unknown solution. It's a function typically of space and time coordinates. Potentially that function, that solution function, should also satisfy a set of constraints, let it be boundary or initial conditions. And the idea is very simple. So we're just going to use a neural net to represent this unknown function U. And we're going to train the neural net actually in absence of any measurements for U, but instead we have we generate virtual training data by trying to enforce that the residual of those equations is 0. So basically the supervision signal that we're providing to our neural net is that it should make predictions that agree with the boundary constraints, but also ensure that the residual of this equation is as small as possible. So basically the loss function now takes a composite form. We have a term here that penalizes the residual of the equation under this neural network representation. And then we have an additional term that makes sure that the outputs of the neural network approximately satisfy the initial and boundary conditions of the problem. So basically, all that happened from 98 to 2017 is just revisiting the same old idea, but now using modern sort of deep learning software. Because somewhere in between, the deep learning revolution started in 2010, and now we have access to very functional and efficient frameworks for implementing those techniques. So we can leverage techniques like automatic differentiation and GPU computing to actually take those ideas and scale them up and try them out in more interesting settings and more interesting problems. So that's what happened in 2017, and kind of revived this idea of using neural nets for solving PDEs or assimilating data with PDEs. And frankly, if you were to take this model published in 2017 and try to deploy it in any realistic application, you would find that it doesn't really work, or things are a little finicky, and you need some sort of additional expertise to actually sort of adapt this physics from neural networks to a given application. So that sort of generated a little bit of frustration amongst practitioners or people that do not have deep learning expertise, and they're like, okay, let me try to use neural nets to solve a PDE. And then they kind of found that it doesn't really work very well in certain scenarios. So since then, there has been a lot of work in this area, try to understand what are the modes of failure, what are the challenges, what are the fundamental differences between training a neural net for regression, where you actually do have labels for this output function that you're trying to approximate, versus training a neural net to solve a PDE. So there's some fundamental differences there that kind of require people to revisit the formulation of the problem and the design of those architectures to address those issues. So recently we had a paper out that would kind of summarize the lessons that we've learned over the last couple of years working with physics-informed neural networks, and basically provide a guiding principle for practitioners to diagnose pathologies and problems, and also to kind of use best practices when training those models. However, today the topic of the talk will be on more recent work, where we introduce a new type of architecture and a new way of initializing those models that is specifically tailored to this type of PDE problems. All right, so let me move on and maybe start from, I just already discussed briefly kind of the problem formulation. So I'll just skip this slide quickly. And I'm going to give you an example and maybe a few take-home messages that will motivate the talk, today's talk. So this is sort of like a toy problem. It's a one-dimensional nonlinear partial differential equation. It's called the Allen-Cahn equation. It contains a diffusion term and a nonlinear reaction term. And if you were to employ physics-informed neural networks and try to solve this equation, you get some results. It's considered to be not an entirely trivial problem for PINNs to solve, but you can make it work. But there's an interesting observation that it's not intuitive from a deep learning point of view. And the observation is that if you start scaling up your model size, if you start increasing the number of layers, so typically in PINNs, people employ the standard MLP architectures. If you start making the model bigger, you see that an MLP would just start failing. So the prediction error is going to get worse and worse. And of course, you may think, okay, we know from deep learning that deep models might have gradient pathologies, vanishing, exploding gradients. Maybe we should use those ideas of using residual connections that were introduced to kind of mitigate those issues. And if you were to do that and switch from an MLP to ResNet, you sort of still see the same trend. So the performance, the accuracy doesn't get any better. Training gets more finicky, more difficult. So there's this counterintuitive observation that deeper architectures, when used for solving PINNs type of problems, tend to fail. So the bigger the model, the deeper the model, the worse the performance, which is very counterintuitive. This is not what we know from deep learning. And adding skip connections doesn't seem to help, doesn't seem to resolve this issue. So today I'm just going to revisit this and introduce this framework of PirateNets that actually can enable us to build deep neural networks for physics-informed deep learning, and it's actually scalable, and its performance keeps improving with the increasing depth, and it's more robust. All right.
Paris, sorry, we have a question from the audience. I can read it from the chat. So, membristors or solitonic metamaterials, quasi-crystal lattices solved for PDE as analog circuits for hybrid systems. Thoughts on their use in analog computing future of physics models? So I think the question is about like using different realization of the hardware with advanced materials in the form of such a way that you can have an analog computer that then simulates the PDE.
Yeah, I think potentially yes, although I think that's a question that's probably better to take offline. I think there's a lot of layers to it that we need to
this is the point is that where physics is analog, we're trying to fit it into a 1 and 0 square peg, you know what I mean? So if we start with analog, we instrument analog, we compute analog, we're going to skip a lot of the steps that are problematic in what you're describing.
Mm-hmm. Well, I'm not entirely sure if that will be the solution, and maybe we can talk about it towards the end of the talk when we can revisit this. I think there's a more fundamental issue with this physics-informed neural network type of models that I will discuss in a little bit, and has to do with how the derivatives of those networks behave and how we initialize them in practice. All right, so let me jump into it.
Okay, so I think we have another question maybe related to this slide. Mm-hmm. So the question is, why does the divergence in error take place in MLP and ResNet with depth?
Yeah, we'll see.
Is it related to higher order differentiation, the problem of error difference?
No. It's not related to higher order differentiation. It's related to the initialization of the model and then how that affects the behavior of the neural network derivatives. And we'll see that in a second. So let me jump to the next slide.
Yeah, Paris, do you prefer to take the questions at the end?
Perhaps, I guess, I mean, I leave it up to you. Yeah, maybe at the end would be easier.
Okay,
I cannot see the
let's do
chat.
that then. Okay.
All right, so now the question is, how can we train deeper pins effectively? And let us just start by revisiting the formulation. So we're given some PDE with boundary and initial conditions. This is the composite form of the loss function. So one claim that we're going to make, and we have some theoretical proofs for that, for sort of linear problems in some canonical settings, is that if we manage to train this objective and push this loss down to 0, then obviously we would expect for a well-posed problem that the neural network should approximate the target solution of the PDE, but also the neural network derivatives should approximate the derivatives of the true solution. So basically the claim here is that if we manage to optimize the loss to convergence and actually drive it down all the way to 0, then the network derivative, so let's say the kth derivative of your neural network, should converge to the kth derivative of the true solution. So this is the first question. Is this a true claim? And the answer is yes. We can prove that exactly for some canonical settings. So for instance, if we consider second-order linear elliptic PDEs, I'm not going to go into the theory, but actually you can actually prove that you can bound the approximation error for the solution and its derivatives to some constant times the value of your loss function. And the same thing holds for, say, second-order linear parabolic PDEs. So sort of as a high-level claim, this, at least in these canonical settings, this sort of makes sense if you were to choose the appropriate norms for measuring convergence. And that's something you should expect. For a well-posed problem, if your loss function is 0, then the neural net should approximate the target solution, and also the derivative should approximate the derivatives of the true function. So this is sort of the mental roadmap, starting from this claim, namely that convergence of the training loss should imply the convergence of the derivatives of the network. We're going to actually start looking at the trainability properties of the derivatives of a neural network. So we're going to actually see how the behavior of the derivatives of a neural network will actually determine whether our PINS model is easy to train or not, and whether it converges to the right solution. And then based on that, this will give us some motivation, and we'll use that as a proxy. So there's two elements here, right? We could actually study how the derivatives of a neural network behave, or we could study how the PDE residual behaves. That, of course, involves evaluation of the network derivatives. However, studying directly the PDE residual may not be straightforward for more complex PDE operators, for nonlinear PDEs. So we're going to use the behavior of the network derivatives as a proxy for understanding how the PDE residual behaves. And then through that, we'll try to build some intuition and try to understand those scenarios where those PINS models are failing. All right, so let's talk a little bit about initialization of deep MLPs, because that's a fundamental element that has been sort of overlooked in the neural network literature. We know it's extremely important for training neural networks. Especially, we know that before 2010, people didn't really know how to train deep neural networks because they didn't figure out how to get the initialization right. And there was a very sort of seminal work by Gloro and Bengio in 2010 that shed some light on how the initialization scheme used to initialize the weights of the neural network plays a role in ensuring a stable propagation of information through the forward pass, but also a stable propagation of the gradient signal backwards in the neural net. And this is essential for training deeper MLPs, so getting this initialization right. So this is overlooked when it comes to PINS because the assumptions under which the results of Gloro and Bengio were derived were the following. So the first assumption is that you have a regression problem where you have input and you have output labels, and then you take your inputs and your outputs and you standardize them to 0, mean, and unit variance. And then based on that, you come up with this initialization scheme that kind of preserves the variance of the signal through the forward pass and through the backward pass. But now the key differentiating aspect between a standard regression problem and PINS is that in regression, you do have access to output labels, and you can use them to compute normalization statistics and normalize them to 0, mean, and unit variance. But in PINS, you don't have any output labels. You're trying to infer a latent function that is a solution to a PDE, but you don't have any measurements of that function at initialization. The only thing you have access to is that this function should give you 0 PDE residual. So the fact that we don't have access to those labels, we don't really have a proper way of coming up with an appropriate initialization for a PINS model. So even though in the literature, everybody would go ahead and just employ blindly this Glorot initialization scheme, it doesn't mean that it's the right choice for a PIN model. And that's something that we need to revisit. All right, so let's see now if we were indeed to do what everybody does in the literature and adopt the Glorot scheme and try to use it to initialize our neural network. Let's see how the network derivatives behave at initialization. So actually, for a plain MLP, we can derive analytically what the expression of the network derivative should look like. And if we actually make a simple approximation, namely that we use linear activation functions instead of non-linear activations, we can actually see that the derivative of the network is basically a product of the weight matrices. So in some sense, your derivative of your neural network at initialization behaves like a deep linear model. Even more so, if you were to increase the number of neurons, if you were to increase the width of your neural network, you can show that the variance of your outputs for the derivative becomes constant, meaning that basically you approximate linear functions at initialization. So the derivative of your neural network is a constant or just a linear function at initialization. So the take-home message here is that for the derivative network, the derivative of a network, all weight matrices directly contribute to the final output, whereas for just the outputs of the network, it's only the last layer weight matrix that contributes to the final output, essentially. The other take-home message is that deeper networks behave as deep linear models, and that makes them sort of the derivative of the network is more vulnerable to vanishing and exploding gradients. And then MLP derivatives tend to be a constant in wider networks and imply that the network is closer to a linear function at initialization. So you sort of like lose some of the capacity of approximating derivatives due to that. So the message here is that conventional neural network initialization schemes like the Glorot scheme will result in this kind of pathological initialization of the derivative of a neural network. And therefore, when we're trying to use them for PINs, when we need to compute PDE residuals, we might be in trouble. So, but before we go to PDEs, let me give you a toy example in regression just to see how these MLP derivatives behave in practice. So here's a toy problem. We have a function in 1D. We generate some training data by observing this function in 256 locations. We're going to now train not the neural network to approximate the data, but we're actually going to train the derivative, the case derivative of the neural network to approximate this data. And we're going to try to test the first derivative, the second, and the fourth derivative, and see whether the derivatives of the neural network are capable of approximating this very simple sinusoidal function. All right, so before we run the training, let's actually first see how does the variance of the first derivative behave at initialization as a function of the width of the neural network. That sort of confirms the theoretical result from the previous slide, showing that as the width of a neural network is increased, the variance of the derivative of the network shrinks at initialization. So it just goes down to 0, implying that at initialization, the network derivative is just a constant function. And this is regardless of the choice of activation function that you're using. Now, the second observation is again, the variance, not just for the first derivative. What we're plotting here is the first derivative. This is the variance of the function itself, so the outputs of the neural net, which sort of stays in a reasonable range and doesn't go to 0. But then the variance of the derivatives, the first, the second, and the fourth derivative all decrease at initialization. So basically, your neural network has some capacity to approximate a function, but it loses its capacity to approximate derivatives. And this is what happens when we actually solve the regression problem. So we take the kth derivative of a network and we try to fit it to the observations yi, and then we compute the test error at some on a test data set generated by the same function. And you see that while the neural network itself, which is U, this is just that the neural network itself has some decent accuracy, and the accuracy is not affected much by the depth. Once we start using the derivative networks to approximate this very simple function, it's kind of hard to attain good accuracy. So the higher the derivative order, the worse the accuracy becomes as a function of depth, which sort of indicates that the derivatives of a neural network don't really have the capacity of approximating even simple functions like sine of 2 pi x if we just use the Gloro initialization. All right. So this is now the question, leads to the question, how can we resolve this and how can we ensure that the derivatives of a neural network have capacity, enough capacity to approximate more complex functions? So for that, we introduced this architecture, this building block that we call PirateNet. It stands for Physics-Informed Residual Adaptive Network. And it has a few elements that I would have to unpack. First of all, we have some inputs. Typically in the PINN setting, these inputs are space and time coordinates. First, we take those inputs and we pass them through some sort of positional embedding or coordinate embedding. The choice that we employ in this work is just the standard sine and cosine positional embedding using a trainable matrix B. Then we have two gate operations. So basically we take these phi of x features and then we pass them through a linear layer in activation and we obtain these feature maps U and V that we're going to use later on inside our main blocks. And then we introduce this adaptive residual block that basically receives the inputs. It performs those two gating operations that you see here. And then finally, there's a residual connection that is modulated by this parameter alpha, which is a trainable parameter that basically gives us the final output, which is alpha times the representation HL plus 1 minus alpha times x, which is, this is the skip connection, the residual connection. So this is what we call the PirateNet block. We're going to build an architecture by repeating this block n times. And that constitutes the architecture that we're introducing. So this is one key element, the architecture itself. The second key element that I will discuss in a little bit is how we're going to initialize this architecture. So we have what we call the physics-informed initialization, but I'll get to this in a second. And finally, keep in mind that the final output is just a linear layer after this n PirateNet blocks. We're just going to apply a linear layer to obtain our final output. All right, so this is again spelled out what happens inside the adaptive residual block. Again, there's these two gating operations, and then finally there's this adaptive residual connection. Alpha here that modulates this residual connection is a trainable parameter that will determine the level of nonlinearity in its residual block. And basically, if you set alpha equals to 1, you kill the residual. There's no skip connection, and basically you just have HL as your output. Or if you initialize, or if you set alpha to 0, then the PirateNet block becomes the identity block, because basically you're killing what happens inside the PirateNet block, and you're just carrying over the input XL. So for alpha equals 0, the PirateNet block becomes the identity map. And that is going to be crucial when I discuss the initialization in a second. All right. And in fact, in reality, we're going to indeed initialize. Alpha is a trainable parameter. You can have it to be a scalar for every block, or you can have it to be a vector with the same dimension of HL. And we're going to initialize it at 0. So basically, at initialization, those PirateNet blocks will act as the identity map. And if we do so, we're going to obtain this approximation at initialization. If we set those alphas to be 0 and we use this PirateNet architecture, regardless of how deep the architecture is, at initialization, we're guaranteed that the outputs of our neural network are just a linear combination of our input coordinate embeddings. So basically this basis phi of x. And again, as I mentioned in this work, we're just going to use sine and cosine as our basis. But you could use something else in practice. And this is where sort of PirateNets intersect with numerical methods. You may use a different type of numerical basis for building these coordinate embedding features. And now the question becomes is how we're going to initialize these last layer weights. Our final solution now is a linear combination of these basis functions. And the way we're going to initialize the weights of this last linear layer is by solving a least squares problem for fitting some data y. So now what could this data y be in practice? These are different potential data sources. If we have any measurements of the target solution function, we can use those experimental measurements. It could be some solutions from some other surrogate model, or even in the absence of any measurements for the target solution function, we could actually try to solve the linearized PDE and use that as our targets, or we could just use the initial and boundary data as our targets. So for any PDE problem, to ensure well-posedness, you must specify appropriate initial and boundary conditions. You could actually use the value of your target function at the boundaries as these targets y, and then to solve this least squares problem to obtain an initialization for this last layer matrix W. So again, at initialization, you just have a linear model. This is how you initialize the linear model. But then once you start training, effectively, you're going to start training this adaptive skip connection parameter, which from 0 is going to take some other values. And then gradually, you're going to start activating these residual blocks that will basically give you your neural network, your kind of nonlinear approximation. So after training, your final outputs will not be a linear model anymore. And from that point of view, the PirateNets will offer an optimal initial guess, because for a PDE problem, the only thing you know at initialization is the boundary conditions. So this is the only available data you have. And through this initialization, you're guaranteed to have an optimal initial guess, at least in the L2 sense. All right, so, and this basically summarizes what I just mentioned. So the PirateNet is initially a linear combination of a chosen basis. And effectively, this addresses the issues of deep MLP derivatives, because we can just take derivatives of these bases and those derivatives do not vanish or do not become constants. And the PirateNet approximation capacity as a neural net is gradually recovered during training, thanks to the trainable parameter alpha that will be gradually activated through gradient descent once we start training the model. All right, so some results. And these are the questions that the results are aiming to address. First of all, is the physics-informed initialization helpful? Is the adaptive skip connections helpful? Is the gating operation helpful? So these are all basically choices that we made in designing this architecture. And then finally, can actually PirateNets facilitate efficient training of deeper PINN models, and whether it can actually yield better results than what has been reported in the PINNs literature? So we're going to start with building some baselines. I'm not going to go through the details, but I mentioned earlier in the beginning of the talk, this paper that we have on, we call it an expert guide for PINNs, where we have all the best practices. So basically, we're going to take the strongest baselines from that paper. And, there's a lot of jargon here that you may not be familiar with, but all I'm trying to say here is that we're going to take the strongest possible baseline that we have for PINNs, and we're going to use that to compare the results that we get for this PirateNet architecture. So I'm going to skip this detail. There's a lot of tricks that go into play when it comes to PINNs for training them. All those are summarized in different papers. And if you want to find a resource that has all those tricks collected, is this experts guide paper that I mentioned. But the main message here is that we're going to be comparing against the strongest possible baseline that we can come up with. All right, so now revisiting this Allen-Kahn equation, there's a few ablation studies that I want to highlight. The first ablation study is on the choice of data for solving the least squares problem for the initial condition. Sorry, for initializing the last layer weights. As I mentioned, there's different choices for target data for this least squares problem. You could use the initial conditions of the PDE, or you could actually solve the linearized PDE and take the solution of the linearized PDE as your targets. This is how the linearized PDE would look like in this setting. And basically, this graph shows that it doesn't really matter. So the initialization scheme is not so sensitive on the type of data that you're using to solve the least squares problem. And you can actually just use your initial and boundary data to initialize the weights of the last PirateNet layer. The second ablation study has to do with what is the effect of the physics-informed initialization, what happens if we do it or if we don't do it. And this is initialization that you can apply to any other architecture, not just the PirateNets, but even a standard MLP. And you see that indeed it has an effect. So for both PirateNets and what we call a modified MLP architecture, using the physics-informed initialization gives you quite a bit of a bump in terms of the test accuracy. And then finally, you see what happens as we increase the depth. The PirateNet performance consistently improves with increased depth, whereas just an MLP architecture struggles. And that goes back to the issues I described earlier, that MLPs will have this difficulty for these PINNs type of problems as the depth is increased, because the derivatives of those networks are ill-behaved under the Gloro initialization. This is basically how the prediction would look like. That's the reference solution that we're solving for. And again, remember that the training data consists of measurements of the solution at the initial condition. So there's basically this boundary and then the boundary condition. So basically the top of this domain, the left of this domain, and the bottom, plus collocation points for enforcing the PD residual inside the domain. So this is sort of the training data. This is the reconstructed solution through this PirateNet model, and this is the absolute pointwise error. Okay, some curves that show the convergence of the different components of the loss function. We have an initial condition loss, the PD residual loss, and then the test error convergence. And again, you see that the PirateNet gives some improvements over the strongest baseline that we had available to compare against. And this is the evolution of the adaptive skip connection parameters. Remember, these are initialized at 0. And then during training, those are activated and basically turn on the nonlinearity of the neural network. And finally, they just converge to some plateau values. And this is the comparison against basically the state of the art. This JackSpy library is what my group has developed, and it corresponds to this expert guide paper that I mentioned before. So this is sort of the modified MLP. The blue curve that we're comparing with here is this result. And then there's other methods proposed in the literature for this problem, and you sort of see the best performance that has been reported, and PirateNets is currently the state of the art. A few more challenging examples. This is again another diffusion reaction equation in 2D. It's called the Gray-Scott equation, and this is an example for which we were not able to make PINNs work before. None of the baselines we had available to us could work for this problem. It would totally fail, and you can see here that the error for the two variables u and v for an MLP method, again, this is the strongest baseline we had access to before we tried PirateNets. The error was, almost 100%. So this benchmark caused complete failure for PINNs. Whereas this PirateNet architecture seems to be robust. And you see here basically the convergence of the test error for two different choices of activation functions. And it seems that the Swiss activation does a little better, but even the hyperbolic tangent also works fairly well. The spiky behavior you see here at the loss is because we employ what we call a curriculum training. This is a time-dependent problem, so we kind of like split the time domain into time windows, and then we train the model within those time windows before we move on to the next time window. So it's kind of like a sequential training over time. And every time you see a spike in the loss is when we transition to the new time window. A few more ablation studies in this case. As a function of the depth, we see the test error for two different choices of the initialization of the alpha parameter that controls the residual connection. So we could initialize alpha to be 0, which is the choice we recommend, which makes the model behave like a linear model at initialization. Or one might think, what happens if we initialize the parameter as 1, which basically will kill the residual connection and just, it will be a feed-forward network with no residual connections. And you see that that doesn't work. There's quite a big difference. The y-axis is test error in the log scale, so it's orders of magnitude worse. And then the second ablation here is what is the effect of these gating operations. The effect is not huge. You see, you still get pretty good accuracy in terms of test error, but there is some improvement, some small improvement if you introduce also these gating operations in the architecture. So it's not crucial, but if you're looking for state-of-the-art performance, it can make a little bit of a difference. A few more examples for which PINNs are struggling with. It's this lid cavity flow problem. It's an incompressible Navier-Stokes fluid flow. And here the Reynolds number is a parameter that we can control to modulate the complexity of this problem. So PINNs have been successful in solving this problem for low Reynolds numbers up to like maybe 1,000. But as you increase the Reynolds number, it becomes increasingly more challenging to make those neural nets work. So here we're testing a relatively challenging case of Reynolds number 3,200, which, if to my knowledge, I think it's the highest that has, that we have been able to successfully tackle with PINNs in this case. So this is how the prediction looks for PirateNets, and this is a comparison against classical numerical CFD solvers in terms of the velocity profiles across the cavity. And again, another ablation study to see how the model architecture behaves. We're training models with different number of PirateNet blocks, so different depth from 6 to 24. And we see that as the depth is increased, we get some performance gains, although there's a plateau at some point. I think after, from 12 to 18 blocks, we kind of reach a plateau, and we cannot further improve the accuracy by increasing the depth of the model. And then for the case that we're using 6 blocks, this shows the kind of behavior of the skip connection parameters, those trainable alpha parameters. Again, they're initialized at 0, and then through training, they kind of converge to some values, and sort of they activate the nonlinear behavior of the neural network. And you see that for this problem, we have slightly higher magnitude, so sort of the neural net sort of benefits from becoming increasingly more nonlinear to deal with this. So in the paper, we have a lot more examples to look at. I'm not going to go through the details. It kind of gets boring to talk about benchmark certain results, but this is sort of a summary of the results that we get with PirateNets. This is test error versus the strongest baselines that we had access to. The most impressive one, I think, is the Gray-Scott example, for which PINNs totally failed, and now this architecture seems to work quite well. But there's consistent improvements across all the benchmarks we have considered, and here you see also some of the visualizations and animations for different benchmarks. So with that, I'll just try to summarize and take some time for discussion. So we started from the hypothesis that convergence in PINNs training loss should imply convergence in the derivative of the neural network. Based on that, we studied the behavior of the derivatives of neural networks. We also proved that this hypothesis is theoretically sound for second-order linear PDEs, elliptic and parabolic PDEs. And then through the lens of studying the derivatives of a neural network as a proxy of studying the PDE residual of a neural network, we actually identified initialization pathologies that lead to poor behavior of the network derivatives, and therefore lead to problematic training of the residual loss function. And then we introduced this idea of PirateNets to kind of overcome or circumvent these pathologies by introducing an architecture and also an accompanying initialization scheme that is appropriate for ensuring stable and efficient training of deeper PINN models. So with that, I'd like to, well, some future work is to look into other types of coordinate embeddings. And I mentioned earlier that there is a connection there with sort of classical scientific computing methods, because here we use sine and cosine bases, but one could use any other sort of numerical scheme there. You could think of using finite element bases, spectral element bases. That could enable you maybe to deploy these tools in domains with more complex geometry. And another bullet is to extend these ideas of PirateNets to neural operators and physics-informed neural operators, which could allow you to solve and sort of build PDE solvers and surrogates over a collection of problem instances, like different initial conditions, different boundary conditions. PINNs do not handle that. So in PINNs, if you have a new problem setting, a different initial or boundary condition, you have to retrain it from scratch. However, neural operators can enable you to train over a distribution of inputs and then allow your model to generalize to new scenarios without retraining. So with that, I'd like to conclude, and I think we have plenty of time for discussion, so I'm looking forward to it.
Thank you very much, Boris. Thank you for sharing your work. We do have a few questions in the chat, and we also have a raised hand. So I'll go in chronological order. We've got a question from Matisse. Sorry, this might be a basic question, but what exactly is the gating operation doing? It's a dense layer from the coordinate embedding that modifies the connections.
Yeah. Yeah, so basically this is sort of what the gating operation does. So maybe I can. So first we take the inputs and we generate these two feature vectors U and V, and the gate acts pointwise on the output of your hidden layer, and you perform a pointwise multiplication with U, and then you take 1 minus your activations and you do a pointwise multiplication with V. So this sort of helps in cases where you may have a vanishing signal. So let's say if the activations F become really, really small for some reason, then this kind of, the second term will help you recover and won't allow the propagation, won't allow the vanishing information either in the forward pass or the backward pass. So it's kind of a way for further mitigating any issues related to vanishing information in the forward pass or the backward pass. And as we saw in the results, it doesn't play a huge role, but it does give some small improvements.
Okay, thank you. So we have another question. I understand that the training data does not have to provide samples at the same time instance or a uniform time grid at all. Is this correct?
That is correct, yeah. So it does, the training data is randomly distributed in time and in space, meaning the collocation points that we use to train the model. Yes, that's correct.
Are sign cost embeddings optimal?
That's a great question. So we have actually experimented a little bit with that, and I maybe didn't go through all the details. Let's see if we have it here. So we tried different cases. So first of all, we tried sine and cosine embeddings, where this B matrix is fixed to some values, or could be either just integer frequencies. That worked, and in some cases it gave better results, but it also could lead to overfitting. So generally, what we tend to do is we initialize this B matrix to be totally random from a normal distribution with zero mean, and we allow it to be trainable. Maybe that doesn't give the most, the highest accuracy, but in terms of robustness is a choice that always seemed to work very well. We also try to use other bases, like if I recall correctly, Legendre polynomials. And again, similar behavior, you kind of could get better accuracy, but there's a tendency to overfit, so it's a little bit less robust. So that's an area that we want to look a little bit deeper in the future to understand what is the precise effect of the coordinate embeddings. But a choice that seems to be robust is just to use sine and cosines with a random initialization for the frequencies.
Right. I'll take a question from the raised hand. So does Nikki, you may go ahead.
Hi, thanks again. I'm really excited by all of this great work. I'm the one that asked the question on the memristors and analog. I think kind of my point is that, the history of computing is a history of cogs and gears. And ultimately, all the physics phenomena that happen in computing today are really trying to fit a continuous flowing analog universe into cogs and gear systems that was designed primarily to defeat the Nazis, right? And so that computing model that is representative in our digital systems today is what I'd say 80% of the work you're doing is trying to, make up for the fact that the data sets are digital and not analog, and that the computing is digital and not analog, and the physics is all analog. And ultimately, where there is embedded stochastic differential and partial differential equations is in the current space of memristors. Memristors plus what solitons are, for the folks that don't know in the call, are standing waves that travel. It's like a cymatic vibratory concept, but it's everywhere. It's a fundamental physics phenomenon in all vibrating systems. But the math behind it is the soliton is actually the solution to the sum of all the partial differential equations of that vibrating system. So when you think about what the outcome is of what you're trying to do, you're deep in the engine and fixing a Bugatti, but at the end of the day, people want to teleport. Okay, what we need is the spatial, real-time neurophysics-based system that uses this kind of, fundamental rouliad, I'm going to call it, of all of the computational differential equations that we know, and then in instantaneous real-time analog does what it needs to do, gives you bias detection, translates whatever it needs to do. It does it in analog from analog, And that's where I'm promoting a model where your research looks at how you take neural networks and actually configures them in an analog circuit as a series of pre-existing solitonic quasicrystals latticed together in such a way as to represent all of the sum partial differential equations as in the Rulliad. What is computable could be just a fixed set of predefined solution sets that memristors flow through, and in real time they reconfigure. And so I've got all this written down. I've got architectures behind it. I've got a lot of mathematicians helping me that are vortice and soliton experts and metamaterial and circuit analog experts. So I'm happy to support. But the computer science and the data science that you're doing is to try to fix the fact that everything is based on, you know, this gear system, this digital problem. And so given the fact that most of the solutions that you're going to be building for are sourcing instrumented physics phenomena that are flowing, the basis of that sourcing should be an analog circuit, because we are analog and the world is analog and physics is analog in the universe. So that's my main points. Thank you so much.
Thank you. Yeah, I mean, it all sounds fascinating. It's a little outside of my sort of bubble of expertise, but I'd love to learn more about it. If you could share any links in the chat, that's, you know, that sounds all fascinating to me.
Thank you very much. So we have another question from Carlos.
Hi there. Actually, I have several, but I can start with one. So first, kind of like a point. So for the proof that you had of the pathological initializations, for what I understand, is basically using the idea of like neural tangent kernels, right? Like pushing things to infinite width and seeing how they behave there. Apart from the experiment of the empirical results, do you think there's any way to generalize those to finite widths and still kind of like prove or at least get some kind of limits on these pathologies?
So if I recall, I don't think that you mean the proofs that are the statements here. I don't think these rely on any they don't revoke the NPK or anything like that. I think this.
I was referring in slide 12, actually.
Sorry, 1 second. Slide 12. This one.
Well, no, the next one. I think the number is different. I think between.
Oh, right. Yeah. So yes, I mean the basically the statement here is as the width goes to infinity. That's true. And then we have the empirical results to see what happens with finite widths.
Connection between the two, I suppose, is kind of tricky, right? To kind of get any kind of theoretical results for finite widths.
Correct. Yeah. Although it seems like the kind of intuition holds on the empirical results numerically.
Yeah. Awesome. Well, I've got 2-3 more questions, but I'll let other people go in case they've got any.
Okay, thank you, Carlos. We do have quite a few here on the chat. So there's how is the architecture of the MLP baseline chosen?
Okay, so this is the slide that I went through super fast. How's the architecture of the baseline MLP? So this is sort of what we have presented in that paper that I mentioned. So yeah, this is sort of the baseline MLP. So the baseline MLP employs the same type of coordinate embedding, which is what we call random Fourier features. The architecture itself doesn't have residual connections. It has the gating operations, but it doesn't have residual connections. So by modified MLPs, I mean an MLP that includes the gating operations, but it does not include the residual connections, and it doesn't employ the physics-informed initialization that I mentioned earlier. Moreover, the other trick that is used here is that every weight matrix in the dense layers employs some form of weight normalization. So this is a technique we have experimented with PINNs. It very much resembles weight normalization, and it just adds a trainable scalar that multiplies the weights of the dense layer and allows the magnitude of those weights to change. So it's just a sort of like a standard trick. This is in terms of the architecture of the baseline. So it's pretty much the same as the PirateNet without the residual connections and without the physics-informed initialization. Then in terms of the training algorithm, I think everything employs the same approach. So we have, remember that we have loss functions with multiple terms, and we have weights multiplying each one of those terms. So we have some ways of adaptively adjusting those weights during training, so the convergence of the different terms is balanced with respect to one another. The second piece is this causal training, meaning that we train the networks to fit the solution at early times and then gradually expand the time horizon to future times, so to make sure that we respect the temporal causality structure in time-dependent PDE problems. And same thing for this time marching is what I mentioned earlier, that we split the time domain into time windows and we train gradually, but the training protocol is the same for the baseline versus PirateNets. So the only thing that is different is the architecture.
Thank you very much. Another one. So how do PirateNets perform in inverse mode when PINNs are also estimating equation parameters?
Yeah, so we haven't thoroughly worked with inverse problems. I anticipate that the benefits carry over to inverse problems as well. We mainly focus on forward problems because this is the weakest sort of spot of PINNs. PINNs have a really hard time with forward problems, specifically because you don't have access to labels and target data to initialize them correctly and so forth. So it tends to be that the optimization problem for forward problems is a lot more ill-conditioned compared to inverse problems. So I believe those improvements will carry through to inverse problems, especially in inverse problems. The cool thing is that you do have data for Y here, and this physics-informed initialization should be even more effective. But we haven't experimented thoroughly with it, primarily because it's kind of like an easier setting, and we really wanted to see, the forward problems is where PINNs are struggling the most. So from a research standpoint, it's more interesting to study forward problems.
So yet another one from Yahya. Regarding the generalization aspect, I'm working on a model that incorporates a hypernetworks to condition main PINN weights on exogenous input, which means where the input sequence may not be presented in training data.
Mm-hmm.
Would such training strategy help in stability of training? If anyone is interested in knowing more, I'd be more than happy to share details.
Yeah, so that goes back to this point I had. So yeah, if you want to generalize, using a hypernetwork to condition on different inputs basically opens the door to this whole literature of neural operators, which, neural operators is just architectures that, condition some base neural field or neural operator based on this external input. So you could use a hypernetwork or anything else to build an architecture there. That's something that we want to look into the future. We haven't experimented much in this setting, but it's a natural next step to look into, and I believe the ideas are applicable. We just need to kind of figure out the details there.
So we have one more. I'm conscious of the time. If that's all right with you, we'll skip over for just a few minutes. So if we have noisy training data, would PirateNet work similar to a kernel estimator for a GP?
So can you repeat?
If we have noisy training data, would PirateNet work similar to a kernel estimator for a GP, a Gaussian process?
Basically, the PirateNets is just a deterministic neural net. It doesn't have any ability to give you a posterior distribution. It will just approximate the conditional mean. So it will regress through the noisy data and just you kind of recover the conditional mean, but you don't have any uncertainty estimation.
Are there any specific challenges or limitations encountered in compiling the training datasets for PirateNet, such as data availability, variability in signal characteristics, or ethical considerations?
No, that I don't think it applies, especially for forward problems. There is no training data whatsoever. The only thing you're given is a PDE plus its boundary condition. So it's, from that you go ahead and you train a neural network.
Is it Glorat initialization performing badly, even in case you have availability of several target data in the domain?
No, it should work as long as you use your target data, you normalize them to zero mean and unit variance. That's a setting where, the Glorat initialization was designed for. And that's why inverse problems tend to be a lot easier for PINNs.
Right. if I can squeeze in one tiny question before I hand over back to Carlos. I know you mentioned that in future work you will consider the initial conditions aspect. Currently, why do you hypothesize that your architecture does not generalize for initial conditions?
It's just not designed to do that. So there is no reason why we would expect that this architecture would generalize to, like, if you were to change the problem specification, you would have to retrain it from scratch.
Yeah.
Because basically the initialization will be wrong. And then the model will not fit the new initial condition, right? It's trained to fit another initial condition. So you have to retrain. In neural operators, you would train the model over a collection or a distribution of initial conditions, and therefore then you would expect the model to be able to generalize to a new initial condition within that distribution. But here we train only for one initial condition, so then you cannot really expect that you can generalize.
But I'll make a comment, not a question, as just of an open comment, maybe which needs more discussion, is I find that on this note, I always found that PINNs are slightly superficial in the way they leverage physics, because I feel they're not fundamentally leveraging the fundamental representation of physics. And so I think there are much better ways and much better biases that could be used to leverage, have more structural intent, that are more fundamental. In fact, when you mentioned the coordinate embeddings, potential direction could be to inform those coordinate embeddings to align with actual coordinate embeddings that are informed by more fundamental representative physics.
Yeah, and a good example is, for instance, and I sort of know the answer to this, but only for linear problems. So if you have a linear PDE, you can use the eigenfunctions of your PDE operator as your coordinate embeddings, right? That captures the right information. But for nonlinear PDEs, that might be tricky. But you're absolutely right. I totally agree. And that's sort of like I made that comment early in the talk that, PINNs is sort of the easy way out. We don't touch much the architecture and try to bake in the right biases, but we just try to use penalty terms in the loss function.
Thank you. Thanks for that. Carlos, you got one question and then we will have to hang up.
Okay, then I'll choose wisely. For the computational cost, have you found any case in which with PINNs you can compute a solution to a forward problem faster than with a state-of-the-art like traditional numerical methods?
Not really for just a single problem instance. Like if you want to solve a single PDE, then better probably use a numerical solver, unless there's some peculiarity in the problem. Let's say you have discontinuous solutions, or you have some cases where traditional solvers might struggle. When it comes to computational efficiency, things get more interesting when we move to this neural operator setting, where you can actually solve multiple PDEs very quickly, and that's where you see gains over PDE solvers.
Awesome.
Brilliant.
Thanks a lot.
Carlos, maybe you can reach out to Paris with your remaining questions. I'm sorry to cut you off right here. I'm just
that's fine.
Yeah.
Like already breaking there.
Yeah, happy to take this offline. But yeah, thank you for all the questions. That was great.
Okay,
Awesome.
Thank you once again, Paris. This was really great. And also thanks for the discussion that you generated. Thank you to Andrea once again, and thanks to everyone for joining. And we'll see you again for our next seminar. Thank you.
Thanks for having me.
Thank you, Paris. Thank you.
Bye.